Good day. So, today we will start our discussion on data link layer. As a matter of fact, we have already discussed a part of the data link layer, namely the MAC sublayer, and we will see how that all fits in. But to fit it into the broader picture, if you remember when we were discussing the 7 layer OSI protocol, starting from the application layer, the bottommost layer was the physical layer. So, we have finished our discussion on physical layer, and just above the physical layer we have the data link layer. So, we will look at the different components of data link layer and how they are used, and we will look at a few protocols, etc. So, that is what we will do. So, our main this thing is data link protocols, which are the protocols which are used in the data link layer. Now, what are the main tasks of data link layer? It transfers data from the network layer of one machine to the network layer of another machine. So, actually this is the part of the service it gives to the upper layer. You remember that above the data link layer we have the network layer, alright. So, below the network layer we have the data link layer. So, the data link layer gives some service to the network layer, and this service is the transfer of data from one network layer to another network layer. So, that is the service it gives to the network layer, and this in its turn uses the physical layer. So, it converts raw bit stream of the physical layer into groups of bits, etc., or frames. So, this is how we can look at it. So, this is one node and this is another node. Above this, of course, there may be other layers. We are not concerned about these upper layers at the moment. So, this gets some data to be sent from the network layer, and this data link layer sends it to the next data link layer. Remember once again that the network layer is concerned with transfer of data, etc., across the network. That means, it may take several such hops, but data link layer is just concerned with a single hop. So, this is how we simplify the problem of going multi hop. So, this multi hop part we leave it to the network layer. For this single hop, so multi hop naturally will constitute a number of such single hops, and data link layer would handle the transfer of data from one node to the next one hop. So, actually this is another way of looking at it, because for the there is a virtual data path from layer 3 to layer 3, but actually this goes through the data link layer, and this is the actual data path which goes through the physical layer and some physical transmission medium. Now, why do we require any kind of control in the data link? These are the main points, or these are the main functions of the data link layer. So, actually not all of them or not all combinations are used in all situations, but these are the general sort of categorization of the kind of thing that we would be concerned with in data link layer. One is frame synchronization. That means, when you are the beginning and the end of a data block called frame should be recognizable, alright. That means, when you are sending a number of bytes, let us say, from one machine to the other, so they are sort of grouped into, let us say, some blocks. So, on the other side they should be able to recognize that, okay, this is the beginning of the block and this is the end of the block. Okay. So, for that you need required to organize the these bytes into some what are called frames. So, we will look at details of frames later on. So, that is the first job of data link layer. Second job of data link layer, which it might do or might not do in some cases, but anyway one of the things that it does sometimes is flow control. This sender should not send frames at a rate faster than the receiver can receive and process them. This is important, okay, because if the because the sender may not know everything about the state of the receiver at that particular point of time. Okay. So, if it keeps on sending data which overwhelms the receiver, so the receiver will be forced to drop some of that data. So, in some cases this is ignored, or in some cases this is not relevant, but in some cases these are very relevant and the data link layer may do some flow control. Secondly, thirdly rather, error control. Any bit errors introduced by the transmission system should be corrected. This is important, that whenever you are sort of sending something through a transmission medium, there is always some chance of errors, and the data link layer has to take care of this error on that particular link. We will come to this, say one second. Next is addressing. On a multi-point link like LAN, the identity, that means suppose there is a LAN which is hanging from a bus or something, the identity of sender and receiver must be specified, okay, and the identity, in such a case the identity of the receiver would be very important, because in many such links and especially broadcast links, what happens is whatever you send reaches everybody. Now the receiving station must know that whether or not this particular frame is meant for him. So the receiver, the address of the receiver is important. So addressing, this is another issue, and this is a data link layer kind of address. We will come to that later on. Now for whatever, for all this error control, flow control, maybe etc. So we require some protocol, some data link layer protocol to run between the two layers. All right. So for in order for this protocol to run, actually these two nodes need to exchange some control or management information. Okay. Otherwise, their protocol cannot run at that level. But how will this control or management information go from one machine to the other? How will they interchange? Once again through the same medium. All right. So control and data on the same link. So control and data will flow on the same link. The receiver must be able to distinguish control information from the data being transmitted. Then we require some link management, procedures for the management of the initiation, maintenance and termination of a sustained data exchange. So these are the different functions of the data link layer. So far as services, if you look at the same thing from the services angle, what kind of services it gives, like it gives framing and link access. So encapsulates datagram into frame, adding header or trailer. Okay, we will look at these headers and trailers. These are dependent, what kind of headers, what do they contain, etc. That depends on the particular protocol that you are using on that link. Sometimes some of them do not have any trailer, only header, some of them have both header and trailer, and this is the part which is used for the protocol to run. Channel access is shared medium. We have already seen a number of such cases, the so called MAC protocols. So that is also a part of this. If it is a shared medium, then the medium access control has to be used. And then the addresses, if there are multiple receivers. So these are the so called MAC addresses used in frame headers to identify source destination. This is different from another address we have over the entire network, which is called an IP address. So we will be looking at IP address later on when we talk, after we talk about network layer, but right now the addresses we would be considering are the MAC addresses, also known as hardware addresses. Link layer services, other services is that it's reliable delivery between adjacent nodes. So for reliable delivery, so we may need to something depending on the quality of your link. All right. If the quality of your link is very good, like say some good quality fiber, etc., you may not need to do much. Okay. But then there are media which essentially are very prone to noise or very prone to introduction of all kinds of errors. So in such cases, the data link layer has to take special care so that the transmission over this particular link is reliable. All right. Apart from this particular link, you may still require some kind of resilience at a higher level, because some particular node in between at a network layer, if you are, when you are talking about the entire network, at some particular node in between, the node might fail. So whatever protocol you might be having for data link layer, etc., for making it very sturdy, it will not work. So the chain will sort of break down, but this is to make individual links of the chain as good as possible so far as errors are concerned. So, this is one job of the reliable data delivery. Just as fiber etc. may have low error bits, similarly some links like wireless links have high error bits. Why both link level and end-to-end reliability? So, this we have just discussed. Then flow control, as we were saying, pacing between adjacent sending and receiving nodes. So, they sort of must be able should be in sync. That means, whatever the sending station sends and the receiving station should be able to absorb that much. So, for that you may require some explicit control sometimes. So, we will look at flow control later on in some later lecture. Error detection, errors caused by signal attenuation, noise etc. So, receiver detects presence of errors, that is error detection part. Now, once you detect that there has been some error in this, several things may happen. First of all, you may ask for some retransmission from the other side, so that you can get the correct data, or what might happen in some cases, at least in some limited cases, you might be able to look at that faulty data and correct it locally, okay, without referring back to anybody, or without sort of any reference to the sending node. You can do it locally at the receiving node. So, that is called error correction. So, we will look at that also. So, error detection and error correction, receiver identifies and corrects the bit errors without resorting to retransmission. So, if that we can do that, that is very good. And all these would happen on the line, and the line could be simplex, half duplex and full duplex. Simplex not very common, because simplex can go in only one direction, half duplex or full duplex, maybe half duplex and full duplex. With half duplex, nodes at both ends link and transmit, but not at the same time, we know that. So, what are the kinds of services, type of services that the data link layer gives? One is unacknowledged connectionless. No attempt to recover lost frames. If some frame is lost due to noise, error etc., etc., there is no attempt to recover this, because and there is no acknowledgement from the other side. It is a connectionless system, suited for low error rate networks or for fault tolerant applications such as voice. What do we mean that voice is a fault tolerant application? We mean that even if some of the bits in a voice stream, digitized voice stream, that is, even if some of the bits drop, obviously there will be some degradation on the other side if you are not doing any kind of correction etc. But to the human ear it may not be very perceptible. Okay. For example, I am talking, even if there is a momentary glitch, you would more or less make out what I am talking about, all right. So, that is why in that sense it is very inherently fault tolerant. So, that is unacknowledged connectionless service, that is one kind of service. Acknowledged connectionless service, this is another kind of service. So, each frame is acknowledged by the receiver. So, this is suited for unreliable channel, where so require this acknowledgement for special reliability. Acknowledged connection oriented service ensures that all frames are received and each is received exactly once, and these services are accomplished using, as I said, simplex, not usual, but half duplex or full duplex channel. So, this is some examples, not very important. Sorry. So, it is a reliable message stream. It may be connection oriented service, or it may be connectionless service. It may be a reliable message stream or reliable byte stream. So, reliable message stream sequence of pages, reliable byte stream, let us say remote logging. So, they are coming byte by byte. Here it is coming page by page. Unreliable connection like digital voice, unreliable datagram. So, these are, but when you come to datagram, this becomes connectionless service, unreliable datagram, acknowledged datagram, request reply etc. Now, let us look at just one thing, that where does this all this data link layer exactly, where does it exist? Physical medium we understand, it is a cable, or it is this electromagnetic field, this free space etc., or a fiber, so we can see it, we can feel it. But where does the data link layer reside, so to say. Okay. So, usually they reside in the so called network interface card, all right. So, let us say if you have a PC which is connected to a network, possibly it is connected through a maybe Ethernet, there is an Ethernet card or something, or Ethernet NIC as they call it, NIC for NIC, that is network interface card, and that network interface card has a socket where your maybe Ethernet cable will come and plug in. Similarly, there may be other kinds of cards. So, there is a network adapter is there. So, these adapters actually implement most of these data link functions, and it is actually these adapters which are communicate. So, let us say we have a datagram which is coming from a higher layer. This is made into a frame by this adapter card, and then this frame is sent, and this in sending it, this is where the link layer protocol comes into the picture and reaches the destination. These are the two adapters. So, this is the sending node and the receiving node. So, as I said, link layer implemented in adapter, also known as NIC. Examples are Ethernet card, PCMCI cards, which may be there in, let us say, laptops and all, 802.11 cards which are used for, let us say, wireless LAN connection and things like that. So, on the sending side, we encapsulate the datagram in a frame, adds error correcting or checking bits, RDT, flow control, etc. And on the receiving side, it looks for errors or flow control, etc., extracts datagram, passes to the receiving node. Adapter is semi autonomous and communicates directly with link and physical layers. So, it is basically the adapters where most of these data link functionalities are. So, that of course means that adapter will have some hardware as well as maybe some inbuilt software. So, all that is there in that card. Now, we talk about two parts, MAC and LLC. We have already seen about MAC. Actually, the data link layer is divided into two parts. Okay? One is the MAC and LLC, as we will see. So, in any broadcast network, MAC, we know the stations must ensure that only one station transmits at a time on the shared communication channel. Otherwise, they will collide and they will become sort of garbled, etc. So, this is the MAC part of it. The protocol that determines who can transmit on a broadcast channel are called medium access control protocol, MAC protocol. We have seen a number of MAC protocol like TDMA, FDMA, CDMA, and then your token based MAC protocols and so on. We will see a few more in future actually. So, this is the part. So, we have this is the, if this entire thing is the data link layer, then this is divided into two sub layers. So, above the data link layer, as you see, that is to network layer, and below it is the physical layer, and the data link layer itself is divided into two parts. The medium access control part which is the closer to the physical layer, and the logical link control. We have already seen a number of MAC protocols. We will talk about LLC or logical link control today. So, the MAC protocol are implemented in the MAC sublayer, which is the lower sublayer of the data link layer. The higher portion of the data link layer is often called the logical link control or LLC. And this is the broad picture. We have been referring to some numbers like 802.1234 etc. So, this is what the broad picture looks like. So, IEEE 802 is a family of standards for LANs which define an LLC and several MAC sublayers. So, you see 802.1 is some overview kind of thing. So, this sort of encompasses all these. 802.2 is the LLC part, which we will be talking about now. And below the 802.2, we have various kinds of medium access control. We have 802.3, 802.4, 5, 6, and now we have 11, 15, 16, all kinds of there. So, all these are in the data link layer. Above this are the higher layers, and below it are the physical layer. So, this is some of the names for the time being. So, 802.1 gives you an overview. 802.2 is the LLC that we will be talking about today. 802.3 is the famous Ethernet. CSMA CD is the kind of MAC protocol that it uses. We will talk about that later. 802.4 is the token bus, which we have already seen. 802.5 is the token ring, also seen. 802.6 is the distributed queue dual bus. FDDI is the fiber distributed data interface, and there are others. Okay, as new MAC protocols and new systems come up, so they keep on adding to this set of standards, etc. So we will see a few more later. So we have this LLC sitting on top, LLC sublayer sitting on top of the MAC sublayer. So what does that mean in terms of headers and trailers? Well, for LLC, whatever it does, it requires some headers. So when the packet is coming from the network layer, the LLC header is added to the packet, and so it will reach the LLC sublayer on the other side. Then it comes to the MAC sublayer, and MAC sublayer will add its header. It may add some trailer also, and this MAC LLC and the original packet, etc. MAC, the whole thing gets maybe constitute one frame, and then it is pushed onto the physical layer in the network. Okay. So 802 LANs offer a best effort data frame service. Error control and flow control are handled by LLC. LLC run on all three 802 LANs and hides the differences to the network layer. So to the network layer, these different physical layer protocols, whether it is a token bus or an Ethernet, etc., that is sort of transparent to the network layer. The network layer does not bother about it. The data link layer takes care of that. What the network layer knows is that this data link layer, which is sitting below me, is going to give me a sort of as reliable as possible service for sending the data or the packet from this node to the next. Okay. So that service is taken for granted by the network layer, and it does not bother with all the different complexities or all the different variabilities which are there in the lower layers. So LLC adds its header, as I showed, to the network layer packet. It contains sequence and acknowledgement numbers. It might, why we will see that later. Resulting structure goes into the payload of 802.x frame for transmission. So LLC operations are sometimes sort of divided in this fashion. We have a type 1 operation and type 2 operation and type 3 operation. So type 1 operation supports unacknowledgement connectionless service. For the different services, we have different types of operation. Type 2 is connection mode service, and type 3 supports acknowledged connectionless service, etc. So we will look at these. And for this LLC, we have a PDU, or the so called protocol data unit, all right. And this protocol data unit, it carries information. So in it carries some different parts, and the different types of PDUs are there. So the information, this PDU, so it used to carry user data. The control field includes a 7-bit sequence number associated with this PDU. It also includes a piggybacking acknowledgement sequence number. What is piggybacking of acknowledgement? We will discuss later. Unnumbered, like various protocol control PDUs, these 5-bit M fields indicates what kind of PDU it is. Then there are some supervisory PDUs used for flow and error control. It includes an acknowledgement and sequence number and a 2-bit some fields are there: receive ready, receive not ready, and reject, etc. These are used for this may be used for some particular data link protocols. So type 1 operation, we know what it is. The UI of PDU is used to transfer user data. There is no ACK, flow control or error control. The XID and test PDUs support management functions associated with all 3 types of operations. That means type 1, type 2 and type 3 operations. So these PDUs are used for any of these. So an LLC entity may issue a command XID or test. The receiving LLC entity issues a corresponding XID or test in response. So you please remember that even if you have an unacknowledged data, that means connectionless kind of service, even then you will have to test the link, see that it is alright, see that the other side is operating, and then only you can send, alright. So, that part checking the link etc., is still necessary whether you have a connection oriented service or a connectionless service. Type 2 operation support the connection mode service. So, type 2 operation involves 3 phases: connection establishment, data transfer, and connection termination. With type 3 operation, which you remember is acknowledged connection oriented service, connectionless service. With type 3 operation, each PDU transmitted is acknowledged. So, there is an acknowledgement coming from the other side. A new unnumbered PDU, the acknowledged connectionless AC information PDU is defined, because for this acknowledgement. User data are sent in AC command PDUs and AC command PDUs, and must be acknowledged using an AC response PDU. So, we will look at some detail of this later on. To guard against lost PDUs, some PDU which the sender might have sent, it may not have reached the destination, alright. So, if it does not reach the destination, so it may be lost. Now, why it does not reach the destination? Maybe the link failed momentarily, maybe momentarily there was a noise burst which sort of garbled the data completely, etc. For various reasons the data may get lost on the way. So, you have to make that worst case assumption. So, to guard against lost PDUs, since this is a more reliable kind of operation, type 3 operation, a 1 bit sequence number is used. We will see how this is used later on. The sender alternates the use of 0 and 1 in this 1 bit. So, how that helps we will see. And the receiver responds with an AC PDU with the opposite number of the corresponding command. Only one PDU in each direction may be outstanding at any time. So, now let us come to some of the details. First we will discuss framing, and then we will look at some of the way things are transferred. Now, frame synchronization, okay. That is, the two sides must be able to synchronize their operation. This synchronization may be of various type, okay. This suppose you are sending just one bit, one byte or one byte at a time. Now, at that byte level you have to synchronize, or you are sending a series of blocks, okay, each block containing a number of bytes, alright, you are carrying them. Now, where does one block start, where does it end, etc., etc. So, all this synchronization, a higher level synchronization is also necessary. So, frame synchronization is necessary. When data are transferred from the transmitter to the receiver, unless steps are taken to provide synchronization, the receiver may start interpreting the data erroneously, okay. Suppose you have taken the first, say the second byte as the first byte, you will never know that you have lost the first byte anyway, alright. Now, two common approaches are there, one is asynchronous transmission and the other is synchronous transmission. So, we will look at both of these. This is asynchronous transmission. Data are transmitted one character at a time. This is what I was talking about, so an asynchronous transmission. Timing of synchronization must only be maintained within each character. And of course, here the receiver has the opportunity to resynchronize at the beginning of each new character, alright. So, if you use some kind of coding, like let us say if you remember from our discussion about how data is encoded digitally. So, if you are using Manchester encoding, so that there is definitely a transition in the middle of the bit, then you can use that transition time to synchronize between the receiving and the sending and the receiving nodes. So, such synchronization is possible. So, when no character is being transmitted, the line between transmitter and receiver is in idle state. So, it is in idle state. So, there must be some start and some stop. Okay. So, this is the start of a sequence of characters, so data are going, and then we may add some parity bits. We will later see what parity bits are, and then the transmission stops. So, there is a start parity and stop bits. In synchronous transmission, here a block of bits is transmitted in a steady stream without start and stop codes. Actually, I mean in terms of efficiency, asynchronous transmission is not that efficient. So, if you are just sending very small amount or just one or a few characters, then asynchronous transmission may be all right, but when you are doing a lot of transfer, all right, in that case you need to, I mean asynchronous transmission becomes very inefficient. So, for the purpose of efficiency, we need to go for the synchronous transmission, where we send a number of blocks, each block containing a number of characters. So, here a block of bits is transmitted in a steady stream without start and end or start and stop codes. The block may be arbitrarily long, it may be. To prevent timing drift between the transmitter and receiver, clock signal is embedded in the data signal, for example using Manchester encoding. Now, apart from this synchronization of clock for the bit, where does the bit start and end, or especially the middle, apart from that you require another level of synchronization, so as to allow the receiver to determine the beginning and end of a block of data. So, this for synchronization we require this. So, we need to sort of say that this, well, this is where the data begins and this is where the data ends. Every block begins with a preamble bit pattern and generally ends with a postamble bit pattern. That means, for each block it starts with a preamble bit pattern, that is the start of the block, and then the block goes, and then there will be some part at the end which is the postamble. Now, what kind of preamble or what kind of postamble would be there would depend very much on what kind of protocol, what kind of data link protocol is running. All right. So, different protocols have some all will be having different headers and different trailers, or some may not be having any trailer at all. So, here I give some examples. I mean you need not remember all this. But this is just to show you. For example, DECnets, these are the some frames. So, okay, some. So, it is this whole, excepting the body, you see that the body is the part which came down from above, that means from the network layer. The rest of it, all this header, the part which is coming in the beginning and the part which is coming in the end, CRC etc., and they have been added at this layer. So, DECnet's DDCMP frame looks like this. ATM cells, they just have a header, CRC and a body. Then IBMs have had some bisync frame. ARPANET, IMP frame. So, this is sort of obsolete now. ISO's HDLC frame, HDLC, we will look at details of HDLC later on. This looks like this, some specific pattern, bit pattern, then some header, then the body, then CRC, and then again some specific pattern. So, a typical synchronous frame format would have 8-bit flag, which would be the preamble, then maybe some control fields, data fields, and then maybe again some control fields, and then some 8-bit flag at the postamble. Now, for sizable blocks of data, synchronous transmission is far more efficient than asynchronous mode. Asynchronous transmission requires 20% or more of overhead. Okay, it has a lot of overhead. The control information, preamble and postamble in synchronous transmission are typically less than 100 bits. Actually, the overhead is much less here. So, the efficiency of synchronous transmission is very high. So, that is why I said that when you are sending a lot of data, you would usually go for synchronous transmission, which is more common. So, now let us look at the specific things of specific issue of framing. Translates the physical layers raw bit stream into discrete units called frames. So, sender is sending and the receiver is receiving. Sender has sent frame 1, frame 2 to frame n. So, you see n frames are on transit and it is going from the sender to the receiver. Now, how can the receiver detect the frame boundaries? Okay. That is, how can the receiver recognize the start and end of a frame? There are 4 methods: length count, bit stuffing, character or byte stuffing, or pulse encoding. So, we will look at some of these now. Now frames could be fixed length like ATM, all right. So ATM cells are a fixed length, so you know once you have synchronized, you know that they are going to come with in a 53 byte kind of regularity. But frames could be variable length also, in which case we use this byte count, byte stuffing, bit stuffing, generic framing procedure, Manchester encoding, etc. One is the framing the length count. Make the first field, so this is the make the first field in the frame's header with the length of the frame. That way the receiver knows how big the current frame is and can determine when the this frame ends. So if you have a frame 1 is 5 characters. So if you write 5 over here, so 1 2 3 4 5 characters. So you know that this is where the first frame has ended, and the next one, say the 6th byte, is to be interpreted as the length of the next frame, which is again 5, and then this one is a frame of length 8, and so on. So you know where each frame ends and the next frame starts. But this has a disadvantage, so which is that receiver loses synchronization when bits become garbled. If the bits in the count become corrupted during transmission, the receiver will think that the frame contains fewer or more bits than it actually does. Okay. Now this is a problem in the sense that when you are sending them, suppose due to some error etc., the count field itself has become garbled. Now the receiver does not know how many bits are there, so it may make some assumption which may be a wrong assumption. So now it will interpret some other byte which is a part of something else, maybe data, maybe some other control field or whatever, as the length of the next frame etc. So once it loses sync, so everything starts getting garbled. So this is a disadvantage, and this is one reason why this is not used much. You can use a checksum. So you can use a checksum. So we will later on see what a checksum is. We will detect the incorrect frames. The receiver will have difficulty resynchronizing to the start of a new frame. So this technique is not used anymore since better techniques are available. So one of the better techniques is known as bit stuffing. Okay. Suppose so use reserved bit patterns to indicate the start and end of a frame. For instance, use the 4-bit sequence of 0 1 1 1 to delimit consecutive frames. A frame consists of everything between 2 delimiters. So you have this 1 delimiter on one side, 0 1 1 1, and then the frame, and then the other 0 1 1. So this as soon as you get a 0 1 1, you know that a frame is starting, and as soon as you get another 0 1 1, you know that a frame has ended. So this way we can know the beginning or the end of a frame. Okay. Well, obviously I do not know whether that is obvious, but there is a problem with this. Problem is, what happens if the reserved delimiter happens to appear in the frame itself? If you do not remove it from the data, the receiver will think that the incoming frame is actually 2 smaller frames. So you understand the problem is very simple. Suppose this we have the 0 1 1 1 as the delimiter, but the data itself may contain that means data which has come maybe from the user. Okay. This may contain any bit pattern, and actually you have to allow any and every bit pattern to the user. You cannot say that you cannot send the 0 1 1 1 1 because it may be some maybe picture is being sent through a number of frames, and the bit patterns may be absolutely arbitrary. So in that case 0 or 1 1 1 may very well appear in the body of the data. So this is where the bit stuffing part comes. What we do is that we introduce another kind of pattern, let us say the same 0 1 1 1 for each 0 1 1 1 which appears inside, which means that for the preamble and the for the preamble on the beginning and the end, we use this 0 1 1 1, and this 0 1 1 1 this unit appears singly at these two places. In the body of the frame, if 0111 needs to appear, instead of 10111 we put in 20111s. So, if the receiving end sees 20111s one after the other, it knows that the it actually is bit stuffing, and it will reduce it to only 10111 in the body, all right, whereas the preamble and the postamble will appear separately. So, the solution is to use bit stuffing. Within the frame, after every occurrence of 2 consecutive ones, insert a 0. This is another example of a bit stuffing. Okay. So, after every if there is a consecutive 2 consecutive ones, insert a 0. For example, append a 0 bit after each pair of ones in the data. This prevents 3 consecutive ones from ever appearing in the frame. So, some bits have been introduced after every 2 ones in the data, we insert a 0, and the receiver knows that if I encounter 2 ones and then there is a 0, this 0 is actually a bit stuffing. So, this 0 will be dropped from the actual data. So, this way these 3 ones will never appear in the body of the frame, whereas it will appear in the preamble and the postamble. Similar to bit stuffing, we may have byte stuffing. For example, let us say a flag, say some character is there, like say flag, which is also a part of the, it may be a part of a regular header, but this just happened to appear in the body of the frame or body of the packet. So, what we do is that we use this other character. So, that is why these are character introduction. So, that is why it is called byte stuffing. One byte is one character. So, we introduce the character escape character just before the flag. And what happens if escape itself appears in the body? Well, we put escape escape. So, if there are 2 escapes side by side, we know that we have to interpret it as only one escape. If there were 2 escapes in the original data packet just by chance, then actually this will be what will be sent are 4 escapes, and just one after the other, and the receiving side for each 2 escape, it will reduce it to 1 escape and know that this is just a part of the data. Only at the end that will we will get this flag etc. by itself. Okay. If there is escape flag, we have escape 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 flag, escape escape and so on. Okay. So, this is known as byte stuffing. All right. So, we have sort of done a general discussion. So, what I am going to do now is to discuss a very simple kind of protocol which is used quite often, known as point to point protocol. So, this is another example protocol that we will be using. It uses some of the stuff that we have done till now, and then we will go on to other parts of this LLC. So, we will be discussing point to point protocol. So, point to point protocol will have some, so it will send things like this. So, there will be a flag. Okay. So, we will just discuss the details of this later on. So, there will be a flag, field, address field, control field, protocol field, payload. This payload is the one which is actually coming from the higher layers, that means from the network layer, and some of it will actually come from the user, from the application layer itself. So, this is the payload so far as data link layer is concerned, then some checksum and some it ends with a flag. So, this is what the general things looks like. What exactly they are usually and how they are used, I am coming to that. So, in a point to point data link control, we have one sender, one receiver, one link. Okay. So, this is the main one thing, that there is one sender, one receiver, and there is only one link. So, in effect there is no question of any media access control. That MAC part is not very relevant over here, because it is not a shared medium, it is just this is just a point to point link. So, that is one good thing. So, we do not require any media access control, and no need for explicit MAC addressing, that is not required, because there is no question of any address. Whatever you are sending from the receiver side, it is just destined for that other side, that is a point to point protocol. Okay. and then and examples are of course dial up links, which many people use, ISDN lines. So, these are all point to point link. When you are using a dial up link for connecting your computer from a remote location, actually that is a point to point link. Your computer is sort of getting directly connected to the computer on the other side, there is nothing else. So, popular point to point DLC protocols are PPP, point to point protocol, which we are discussing, HDLC, which I will discuss later, high level data link control. So, data link used to be considered high layer in protocol stack earlier, now it has become very common. So, so PPP design requirements, these are given in RFC 1557. By the way, I do not remember whether I mentioned this earlier, this business about RFC, which is very very important in the field of networking. RFC stands for request for comment. So, what is happening is that suppose somebody has got an idea, well, it goes through various stages, I am not going into the details of those stages, but at some particular point of time, some particular protocol or some particular system, etc., they become widely accepted and they get coded into some RFC. And if you want to know the exact technical details of something in the network field, if you know the RFC number, go to the website and get the download the corresponding RFC. They are all freely downloadable. So, you can read them and you can get all the details of any of these protocols, systems, etc., that are used in the network. Now, this particular for PPP design requirements were frozen in this RFC 1557. One thing is that it uses packet framing for packet so these are the requirements. So, it has to frame the packet, encapsulation of network layer datagram in data link frame, carry network layer data of any network layer protocol. So, that is one thing. So, then the network layer, once again, just as in the MAC layer we have seen that a number of protocols are possible, and then now we are looking at a number of protocols in the upper layer, that upper sub layer, that LLC layer also. Similarly, in the network layer also different alternative protocols may be possible. So, PPP has to support all this. So, ability to demultiplex upwards. So, what is meant by demultiplexing? What is this demultiplexing? So, this is the main thing, that it is supporting this different network layer protocols at the same time. Suppose there are two network layer protocols, P1 and P2, okay. Both of them are using the same link and both of them are using the same point to point link. So, it is using the point to point protocol. So, the both of them will send it to PPP. So, that is they will get somehow multiplexed and sent on the other side. On the receiving side, by taking it the receiving node, that PPP system, it will get something, it will know whether it is meant for P1 or protocol P1 on the network layer or protocol P2 for the network layer. So, it is separating out. So, this demultiplexing, this has to be possible. This is one of the requirements. The other requirement is bit transparency, which we have talked about, which must always be there. That means it must carry any bit pattern in the data field. So, whatever you may decide as your flag, etc., but finally all those bit patterns may appear in the data, that is always possible. We require only error detection, no correction at the receiving end, that is another point. So, we need only error detection. Connection liveness, we must be able to detect signal link failure to network layer. So, we must be able to detect whether the connection is live or not. If it is not live, then we must be able to give that information to network layer. So, network layer may decide to send its data through using some other channel. Network layer address negotiation. So, endpoint can learn or configure each other's network address, etc., that is also. So, these are all part of PPP design requirements. Non-requirements means these are not actually called for. So, no error correction or recovery, we have mentioned this. No flow control. So, here it is assumed that whatever the sender is sending, the receiver can absorb that. So, there is no explicit flow control. Out of order delivery is okay. That means you do not care if your packets are going or reaching the destination out of order, alright. Of course, if you are sending it through a particular transmission line, just one link, they are not likely to get out of order, but anyway PPP is not, even if it does because of some strange reason, PPP is not worried about it. No need to support multi-point links. So, that is also not in its agenda at all, it is just point to point. Error recovery, flow control, data reordering, if they are necessary, they are relegated to higher layers. So, now just look at this once again and see what it does. First one is this flag. So, this flag 0 111 111 So, this is the flag which shows the beginning of the frame, and the same pattern shows the end of the frame. Okay. So, they are the delimiter for framing. Address, this address is actually meaningless over here, because sorry, you know that, as I mentioned, since this is the PPP link, whatever you are sending, pumping from one end, it will reach only one destination on the other end. So, there is no necessity for having a separate address field. So, address field is just used all once, does not really serve much of a purpose. Control field also at the moment does not was kept over there, because if it is used for some extending this protocol somehow later, so so this field was there, control field. Once again, this is not used. Protocol, this is used because upper layer protocol to which frame delivered, because whatever frame is coming, this is meant for which protocol. You remember we were talking about that example, that in the network layer two different protocols are running, P1 and P2, and both of them are using the same PPP. In that case, on the receiving end, by getting a frame, you should know that whether this frame is meant for the P1 protocol which is running at the upper layer, or the P2 protocol which is running at the upper layer. Both of them are running concurrently. Okay. And then this check, this is for some the error detection part. How this check is done, that we will see in the next lecture, and the end delimiter. So, some in the data frame, some info, that is upper layer data being carried, or check is the cycling redundancy check for error. So, info is the upper layer data. So, this is the main body or the payload which is being carried. Check is for error detection. It uses byte stuffing. You see that 0, 6 ones and 0, which is the flag. So, this is 1 byte. So, this is 8 bits, that is 1 byte is received now. So, the question is received this same pattern, is it data or is it flag? Well, sender adds or stuffs extra zeros 0 1 1 1 1 1 1 0 byte after each such pattern. So, data byte. So, if it is, if had it been a part of data, then instead of getting one such pattern, you would get two such consecutive patterns, whereas if it is occurring singly, that means that is a frame delimiter. So, two such patterns in a row, discard first byte, continue data reception. Single this thing means it is a flag byte. So, this is the one. So, in the inside the data you have this pattern, the same thing I have shown. So, after PPP, instead of it will send the first this B1, then B2 etc., and then instead of sending one of them 0 1 1 1 0, it sends two of them, and then B4 and B5. Okay. So, this is the byte stuffing which is used by PPP. But there are a few control issues, like before exchanging network layer data, data link pairs must configure PPP link, maximum frame length, authentication, etc. So, we have I think this is a better diagram. So, we can look at this. So, the first the link may be dead, then the carrier is detected. So, it will try to establish the link. For that, they will require some authentication. That means the two sides configurations, etc., that must agree. If it fails to establish, then it goes back to dead. If it gets successful, authentication is successful, then of course the network, it is open, and then there is some transmission of data, and then finally it will terminate. So, for all these there is data exchange. We need not go into the details of this. So, configure request, configure acknowledgement, configure not acknowledgement, that means you have configured this thing is not acknowledged. Some of the options are not accepted. and some of the options are not negotiable. So, this way the two sides communicate and establish the link. We need not go into the details, this is not really necessary. So, this is a very simple protocol, just use byte stuffing and you use this some data, some error detection and the framing. Okay, that is also, this is a very simple but very widely used protocol. In the next lecture, we will look at the details of how this error detection and error control can be done by the data link layer. Thank you.